Hello again. We're going to begin our next unit, which is on improper integrals. And we're going to start our discussion by talking about the fundamental theorem of calculus. Now, this theorem comes in two parts. The first part says that if I have a continuous function on the closed interval from a to b, then let's say there's any function, capital F of x, which would be the antiderivative of that. Then if I take the antiderivative of little f of x from a to b, then I can just use capital F, plug in b, plug in a, and subtract the results. Okay, we've seen this before. This is just calculating a definite integral, so it's no big deal. The second part is the one I want to focus on. Again, I need a continuous function on the closed interval from a to b. So what this says is if I take the derivative, which is what d of dx is, d dx, of an antiderivative, which is what that integral is, then what I'm going to do is I'm going to get back to the original function. So basically, if I take a function and I take the antiderivative and then I turn around and take the derivative again, I get back to the original function. Okay, now notice that in that integral, this is very specific. There has to be a variable at the top of the integral and a constant at the bottom. And we'll talk about what happens when that is not the case. All right, so why does the second part actually work? Well, let's look at what it says, and I'm going to start on the left-hand side. And remember, I'm using capital F of x to represent the antiderivative of little f of x. So little f is the derivative of big F, and big F is the antiderivative of little f. All right, so let's integrate first. Let's talk about just that integral part there, and then I will take the derivative. So the antiderivative of f is capital F, and so once I find that capital F, I'm going to plug in the endpoints, the top one first, x, and the bottom one second, and I'm going to subtract the result. So I'll get capital F of x minus capital F of a. Now I can take the derivative of that, and so if I take the derivative of capital F of x, I get capital F prime of x. But then if I take the derivative of capital F of a, remember that's just a constant. I took a constant and plugged it into a function, and I get a constant as a result. So the derivative of that constant, capital F of a, will just be 0. So all I have is the derivative of capital F, which I know is just f of x. So that's why the second part of the fundamental theorem of calculus works. So here's some examples. Let's say I have the derivative with respect to t of the antiderivative from constant a to variable t of n plus 9 dn. What I can do, according to the second part of the fundamental theorem of calculus, is I can just rewrite that expression that's in parentheses and replace n with t. So I get t plus 9 instead of n plus 9. All right, in this situation here, I've got the derivative with respect to b of the integral, or the antiderivative, from constant c to variable b of p squared minus sine p dp. Well, what I can do again is I can rewrite the expression in parentheses using variable b instead of variable p, and I'll get b squared minus sine b. All right, so now if the variable is on the bottom instead of on the top, what I can do is I can switch the endpoints. And you know from integration that what that does is it changes the sign of the integral. So let's look at a couple of examples of that. If I take the derivative with respect to x of the antiderivative from variable x to constant c of e to the t minus secant t dt, notice that the variable is at the bottom, which is exactly the problem that I just mentioned. So what I can do is I can switch the order, put x on top and c on the bottom, but what that does is it changes the sign of every term in the integration. So I end up with negative e to the t plus secant t dt, and that leaves me with negative e to the x plus secant x. I can just go ahead and replace the variable t with the variable x that's now at the top of the integral. Now let's say I have the derivative with respect to t of variable t up to constant n of x to the fourth plus cosine x dx. Again, the variable's at the bottom of the integral, so I want to switch those. And what that does is it changes the sign of every term. So the x to the fourth becomes negative x to the fourth, the cosine x becomes negative cosine x, and now I'm ready to replace every x with the t that's at the top of that integral sign. And I get negative t to the fourth minus cosine t. All right, so now let's say there's an expression on top, not just a variable. Okay, well, what I need to do is I need to use the chain rule and multiply by the derivative of that expression. So here's an example. Let's say I have the derivative with respect to y of the antiderivative from constant a to expression y squared plus y of the cosecant of t dt. Well, second fundamental theorem says I can go ahead and replace t with that expression at the top, y squared plus y. But the chain rule says that I now need to multiply by the derivative of what I just plugged in. So that would be 2y plus 1. All right, let's say I have the derivative with respect to v of the antiderivative from expression v to the fifth up to constant 7 of the natural log of w dw. Now notice again, this has got a couple of problems. First of all, it's got an expression, and second of all, that expression is at the bottom. So what I need to do is I need to switch the order, which means that the integral changes sign. So now natural log of w becomes negative natural log of w, and now I'm ready to plug in v to the fifth into that natural log, and I get negative natural log of v to the fifth, and I multiply that by the derivative of v to the fifth, which is 5v to the fourth, and I get that as my answer there. So here's some more examples. Let's say there's expressions on the top and the bottom of the integral. Well, what I can do is I can split that integral into two integrals with some arbitrary constant a. I really don't need to know what a is. You don't even need to use the letter a as long as it's a constant and not a variable. So let's say I have the derivative with respect to x of the antiderivative from expression 3x squared to expression x to the fifth of t minus cosine t dt. Well, what I can do is I can split that up. So now the integral goes from 3x squared to some constant a, and then the second integral goes from that same a to the expression a to the fifth. All right, so you know from your properties of integrals that adding those two together is the same as using the integral that I originally started with. But the problem with the original is that I can't apply the second fundamental theorem of calculus. All right, so I've done a good job of splitting that up, but notice now that the first term has the endpoints of the integral in the wrong order. So I'm going to put the expression on the top, which means I change the sign of every term in that first integral. And so now t minus cosine t becomes negative t plus cosine t. And now I'm ready to apply the second fundamental theorem of calculus. All right, so I have that. Nothing has changed in that line. I just needed to rewrite it so that you could see it. So if I replace every t in that first integral with 3x squared, I get negative 3x squared plus the cosine of 3x squared. Then I need to multiply that, according to the chain rule, I need to multiply that by the derivative of 3x squared, which is 6x. Then I move on to the second one, and I replace every t with x to the fifth, so I get x to the fifth minus cosine x to the fifth, and I multiply that by the derivative of x to the fifth, according to the chain rule, and I get 5x to the fourth. So we've gone from some pretty simple examples to some more complicated examples of the second fundamental theorem of calculus. We'll talk about this more. If you have any questions, please let me know, and I will see you tomorrow.